In this video, I will be introducing the line integral. I'm just gonna... Okay, so how do we... let's first start off with a curve, right? So maybe it looks like that. Okay, as a starting point and an ending point, and it may be given by x r, a parameterization r equals to x of t, y of t, right? For t between a and b, right? So if we do this, we just have a curve, right? So what if I now have a surface? Right? I have a surface, looks maybe something like this is a crazy surface. Maybe looks something like that. And down here, again, I have my curve C. Right? So there's my curve C. And right up here's my surface. And what I'm going to do is I'm going to look at all the little heights right here. Right? I'm going to draw perpendicular lines to the xy plane. Right? So this is x, this is y, this is z. That's z, right? And now what I'm going to do is kind of like look at this region in the 3 dimensions. What is the area of that region? That's a question we can ask. Well, first, what you might think to do is to look at little rectangles, right? Where their height right there is f of xy. That's their height. And then each of the little bases, right? It's going to be some distance I'll call ds for right now, for change in arc length. So, how do we find this change in arc length? Well, let's look back to our curve. So what you can do is look at a tiny little change in x and a tiny little change in y, right? I'll zoom it out over here so that you can see it better. So right here, we're going to have our curve, a tiny little change in x, a tiny little change in y, right? And right here, you can see it's almost a straight line. That right there is ds, the base of our triangle right there. So the base of a rectangle, sorry. I'm just going to make the picture bigger just because it looks small. And right there is going to be our curve on the xy plane. Right here is going to be our surface. Right? And right there is going to be all the little heights. Okay? And we just look at that surface right there, and we look at tiny little changes, ds's, and we have heights of f of xy. That's the idea of what we're trying to do here. So here, what we have right there is a right triangle. These are obviously perpendicular. So we're going to have Pythagorean triple theorem. So we have dx squared plus dy squared equals ds squared, or square root of this equals ds. Now, a good thing to be able to do right now is to make this in terms of t. It's right there is a function in terms of t. So what I'm going to do is I'm going to divide by dt squared, multiply by dt squared, right? And out of this I get dx on dt squared plus dy on dt squared and multiply by dt. And this gives me ds. Right? Because I can multiply and divide by the same number and get the same thing out. So, you can't really see it well, but after doing all of this, I got that ds is equal to the square root of x prime of t squared plus y prime of t squared dt. And this is going to be the base of our rectangle, ds by f of x, y. And then you can imagine there's going to be another one beside it, kind of like that. And another one like that. And it's just going along the surface along our curve C. So right there is our curve C. Right up here is going to be our surface, right? And I'm just going along this curve right here. That's our surface, and right there's a curve, and we're just going along it. So, and what we found is that the base ds is given by this, and the height is going to be this. So we have it that f of x ds is going to give us the area of this tiny little triangle, right? This rectangle, this tiny little rectangle is given by this, the area of that tiny little rectangle. But, as you all know, that's not going to give you the area of all of these combined. And in calculus, a common way to sum over infinitely many things is just to integrate. So this is how we'd write it. It's going to be the integral from a to b of f of x of t, right? Y of t times the square root x prime of t squared plus y prime of t squared dt. Okay, so this gives you the area between a curve and a surface, and that's the idea behind a line integral.